talking about now is we're going to talk briefly about formal charge. Okay, what formal charge is. Super, super easy. So I'm going to skip a lot of this. If you want to take a look at what it says on there, I'm just going to jump right down to how do you do it and what does it mean, okay? So a lot of times you can have a resonance structure. And a resonance structure is when you can have multiple ways of setting up a Vesper model, where your double bond shifts, but it's still obeying the octet rule and the duet rule, okay? Where it still works and you're just having your double bond shift and all of the ways work, okay? But a lot of times there's only one way that is the most stable, one way of writing it that would be the most stable way of writing it. And so that's where formal charge comes in. So what you're going to do is you are going to compare the number of valence electrons on the periodic table to the number of dots around that particular atom. And if it's 0 and everything ends up with a 0 formal charge is what we're going to call it, that's actually the most stable form. So this one right here, what we've got is we've got NO2 and then we've got ozone O3, okay? And so you can see the Lewis dot diagram of both of these that are on here, and these are two different resonance structures that are here for NO2. And then here we have two different resonance structures for O3, for ozone. What you're going to do is you're going to take a look at the periodic table, and on the periodic table, we're going to take a look at nitrogen first. And how many valence electrons would nitrogen have? Remember, it's the Roman numeral above that tells you the number of valence electrons. So out of 8, it would be 5, okay? And oxygen, by the way, that way we don't have to come back here. Oxygen has 6, okay? So I'm going to call that the formal way of doing it is from the periodic table. So that's what I'm going to call the formal number of valence electrons. So what we're going to do is we're going to take that formal number and we're going to subtract how many it actually has around it. So in a bond, remember a bond, every single bond represents how many dots? 2. It would be one pair of electrons, meaning 2 dots. We're going to assign one of them to the nitrogen and one of them to this oxygen, okay? And here, I've got one of them assigned to the nitrogen, one of them assigned to the oxygen, and same thing here, in my double bond, I've got 2 of each one. So what I'm going to do is I'm going to count the number of electrons that are going around the nitrogen, dots. And I've got 1, 2, 3, 4. You take the formal number, which is what's on the periodic table, which is 5. So this is what I'm calling the formal number from the periodic table. And you subtract the number of dots going around that element. Okay? And you subtract it. And so in this case, what do we get? 1 or a positive 1, and so what they did is they put a plus right there. Let's try the oxygen. Oxygen has how many, formally, would have how many valence electrons? 6. So I'm going to count the dots. 1, 2, 3, 4, 5, 6. Oh no, there's one more, 7. So you're going to take the formal number, which is 6. You're going to subtract the number that it has around it here, which is 7, and what do you get? -1. Okay? And so that's basically how you're going to work this out. Let's try the ozone. Okay, let's try this one. It doesn't really matter which one we use. Both of these are actually equal resonance structures, unless you can get one to be 0 all the way around, which I'll show you on the next page. They're equal. So we've got a positive, and we've got a negative, and we've got a positive and a negative, and these are equal to each other. So, and don't forget, if there's something funny, like when you work out the Lewis dot diagram for this, the central atom is the one that gets any, I call it strangeness or funniness, okay? So you have everybody else obey the octet rule. Your central atom is the one that's going to be strange, okay? Everybody else will have 8. So let's check this one out. Oxygen, we said, should have how many? 6 formally, so that's your formal number, minus. Here I've got 1 dot for this oxygen, 1, 1, so that's 3, 4, and 5. So 6 minus 5 would give us a +1. And around this one, let's try this oxygen over here. Here I've got 1, 2, 3, 4, 5, 6. So this one will be what? 0. 6 minus 6 equals 0. And that's why that one doesn't have any formal charge around it. If I did this one, I get 1, 2, 3, 4, 5, 6. Don't forget the 1 in the bond. Only 1 from the bond. That's 7. So this one's going to be 6, the formal number, minus 7, which equals -1. Okay? Let's try it on our own now. And this just explains it. So this is in writing. It just explains what I just explained. So let's flip over to the back. And let's try some of these out. Okay. So we're going to try to work out this right here and see what our formal charge ends up being around these two oxygens here. Okay. So we can see that these are called what structures? Resonance. Because, and a lot of times you'll do like an arrow in between them to say that, now they may not be equal. Maybe one of them works better than another one, and you'll see why. Okay. So hydrogen. Hydrogen has how many valence electrons? Formally? 1. And this one only has 1. So that hydrogen is a 0. Let's look at this carbon right here. Carbon has how many valence electrons? 4. This one has 1, 2, 3, 4. From every bond, you give it 1 dot. So 4 minus 4 is 0. Let's do this oxygen. Oxygen should have 6. 1, 2, 3, 4, 5, 6, 7. So this is 6 minus 7, which means it's equal to -1. The formal charge around that oxygen is -1. Let's try this oxygen. 1, 2, 3, 4, 5. 6 minus 5. This one's actually a +1. And they will, if there's a negative, there's going to be a positive somewhere. And this hydrogen is 1 and 1, so that's fine. So I've got a positive, negative right there. Let's try this one. Okay. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. The carbon is fine with 4. Let's try this oxygen. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. My hydrogen's fine with 1 and 1. So guess what the formal charges are on this entire molecule? 0. This one ends up being the resonance structure that is more stable. You know how I told you that in CO2, carbon dioxide, you can have your structure drawn this way, or you can also obey the octet rule. Anybody remember what else you could do to obey the octet rule? Triple bond. Awesome. You could have a triple bond on one side and a single bond on the other side and still obey the octet rule, completely obey the octet rule. Guess which one has a formal charge of 0? This one. Why? Carbon has how many? 4. And how many does this one have around it? 1, 2, 3, 4. Oxygen should have 6, and that has 6, and so does that. Why does this one not work as well? Because if you count this one has how many going around it? 1, 2, 3, 4, 5, 6, 7. So you're going to do 6 minus 7, and this formal charge would be a -1. So what do you think this side's going to be? A positive. Okay. All right, and that's the end of formal charge.